All right, line Y1, learning task 2, we're going to take a look at three-phase motor operation. Particularly what we're going to take a look at is we're going to take a look at the way that we develop this rotating magnetic field that we are going to then use to go and create the motor rotation. Ultimately, as we have said before, we have got a two-part machine. We're going to go and have the stator, which is going to go and act as the primary of a transformer. It is going to go and create a rotating magnetic field, and then that rotating magnetic field is going to go and cut across the rotor, which is going to be mounted in the center, creating currents inside there, and those currents that are inside there are going to go and drag the rotor along behind in the same direction as our rotating field. Now, no matter what type of three-phase motor that we're going to utilize, whether it's going to be squirrel cage induction motor, whether it's going to be wound rotor, or whether it's going to be synchronous, they're all going to go and do the same thing. They're going to go and follow a rotating magnetic field around the outside of the actual stator itself. So let's start by taking a look at how we develop that rotating magnetic field. Over here, they gave us a drawing that shows a simple two-pole motor stator. And by two-pole, they mean the fact that they have got all three of these that are going to be norths that are opposing all three of these that are going to go and be souths. We have got all three lines working together to go and create that single pole that we have off of there. The way that we are developing all of our lines of flux inside of here is just going to go and follow a standard. What we're going to do is we're going to go and use left-hand rule to develop lines of force so we know where our norths are and where our souths are, and we're going to go and utilize this drawing over here. And you'll note that this drawing does not have a voltage off of it. This is just current. So we're talking about anytime that I've got current that is in the positive direction or current that is in the negative direction. Anytime that it's in the positive direction, we're going to say it is flowing into our motor. Anytime that we have it in the negative direction, we are going to go and say that it is flowing back out of our motor as well. And we're going to utilize those values to go and establish, our left-hand rules to figure out what's rotating where. Let's start with our very first one here. Well, actually, before I do that, I'm going to come back to this one here. This one here is a Y-connected three-phase stator. You can follow it through as being a Y just by tracing each of the individual lines. So here's my A line, here's my B line. Come back down onto there, and here is going to go and be my C line. Coming back down onto there. So that ultimately all three of them are going to be connected together to go and form this Y type of connection. It does not matter whether we are going to be looking at a Y connection or a delta connection. We are going to go and create the same rotating magnetic field. It's just easier for us to go and explain this thing working off of the Y connected motor rather than working off of the delta connected motor, because we're only examining a single in and two outs, or two ins and a single out off of it. So don't worry too much about if it's going to change if we're operating in delta. It doesn't. You can take my word for it. If not, you can look up other ones on it. We're just going to go through the simple steps of how we create a rotating magnetic field, and then after that, everything is going to be we just take it for granted that this is going to happen inside of all of our motors. Okay, we're going to start here at point number 1 inside of the cycle. And point number 1 over here, we see that we have got a positive or an in value of current on our line A. We've got out values of current that are going to be on my line B and my line C. If you take a look at line B and line C as well, they're only going to be halfway up, whereas A is going to be at a full peak, meaning that we're bringing more current in on A and we're taking out less current on both B and C, but it is still going to go and satisfy Kirchhoff's law of current, which is going to state that when we bring current in, we need to go and take the same current out. We're just going to split it and take it into two currents on the way back out of this. Using your left-hand rule, you should be able to establish your north and south. So you're going to go and take, not the left-hand generator rule, but the simple one where we're just going to curl our fingers around in the direction of our current flow. So looking at this, we see we've got current flow like that, and then the current is going to go down here, and then it is going to go and flow through like that as well. And what we'll see is that we create a north pole over here, which would mean that this opposite side would have to be a south pole, and this would have to be, a north pole over here. Remember that my motor needs to go and use the stator, and it needs to go and use the core that is built on the stator to complete its lines of magnetic flux. If I take a look at the lines of magnetic flux that are generated from here, they're going to enter in, and then they are going to go and travel back up and around. Same with these ones here are going to go and enter in travel back up and around. And we do this on purpose. We want to have these poles that are sticking out because that's going to go and focus our lines of force. So we're going to have a whole pile of lines of force coming out here and a whole pile that are going to enter in over here. That's going to go and give us our current on A. I'm just going to erase a bunch of this so we can get our other currents off of this as well. That gives us our current that is coming in on A. Once A finishes going through its windings, which we have traced through, we saw that it went through these windings, then it enters into here. A is then going to go and hit this point over here, and at that point, Kirchhoff's law of current is going to come into effect, and my A current is going to go and split. Some of it is going to go up to my B, where it is going to come around the back of that one and then head in that direction. Once again, you can left-hand rule to go and form that north. Then the B current is going to go out along this dotted line, around the back, and in like that. Once again, you can left-hand rule, and you will see that you're going to go and have your north over here, so that's going to be your south. After that, the current is going to go and exit on our line B, and then if we go down here, we still have to analyze this one here from my line C. Line C is going to be doing the same thing. We're going to have current that is going to go and enter in over here, and it's going to go around. We see that we can left-hand rule, establish that north over there. Once again, this is going to come around here. We are going to go and establish that south over here because we got the north over there, and then it is going to hit this, and it's going to come back out of my motor. Altogether, what we are going to have is we are going to go and have the maximum amount of flux that is going to be centered right over here because we see that all the current goes through here. Therefore, this is going to have the greatest amount of magnetic flux. Flux is directly related. Remember that phi is equal to ampere turns. And each of these windings has got the same number of turns. This one over here that is carrying the bulk of the current in, all of the current in before it splits up, is going to go and have our high amount of flux. So we're going to have strong flux in the center, weaker fluxes over here on the side. That's going to be our point number one. Point number two, we're going to then move on to this one. Here, we'll highlight that one. At this point, we see that we are still going to go and have A that is putting current in, but it's dropped the amount of current that's putting in. B is now going to be putting current in. And C is going to be taking current out at a maximum. Stick a double arrowhead on here because it's taking current out at a maximum. Same deal as what we had before. We just trace our arrows. This one's going to be going through like that one. Follow that one through down here to the bottom, going through like that one, and then it is going to go and enter into this common Y point. We'll take the B current. The B current is going to be traveling through like that, creating our north pole, traveling through like that, creating a north pole there, which results in a south over there, and then it is going to go and travel down and into this Y point. At this point, we then have got two currents that are going to enter, and they're going to go and form a larger current that is then going to go through to here. It's going to be your double current. That goes through and around, and then once again, a double current through here, and then back out. And so we see that we are now going to go and have our maximum current that is going to have shifted over. Before we had the center of our field, looking at the whole north pole, on our first step, we saw that we had the center of the field over here. That was north with this field centered around the middle one. Now we have shifted it over to the next one over here. We'll go one step further. I'm not going to go through all 6 steps of this because, to be honest, you can go through all 6 steps of this and it's just going to continue on in the same pattern. But we'll go one more here just to, cover off the bulk of it. Point number 3. At point number 3, we have now got B, which is going to go and have current heading in, and we are going to have A, and we are going to have C, which are going to have current heading back out. So A and C each have current heading out, but B is going to be at a maximum, so we'll stick that one there as being the double current, that is going to be heading in. So we'll trace around that double current. Over here we see that we got the double current, we got the north pole, it is then going to go through here, we're going to create a north there, which is going to give us a south over here, and then that double current is going to go and enter into our star point. And then over here, it's going to hit that node. Some of the current is going to go up here, and some of the current is going to go out over there. We'll follow the current up to the A line. The A line is going to be going through like that. You can once again create, using your left hand, a north pole. And then you can go and trace this one as well. You should see you got the north pole there and the south pole over here. That carries it out on the A. We'll still finish up the line C. Line C, we would be heading in. We'd be heading across over here, around on C, and heading in like this. And once again, you can create your north pole here, you can create your south pole over here. And then the current is going to go and head out. We see that our strongest pole is going to be the one with the double current, ampere turn. That's going to be our B over here. And we see that once again, we have got our north pole centered over here. Remember that for every action, there's an equal and opposite reaction. So if we're forming north poles, we are also simultaneously going to be forming south poles. From this point, we can go on to point number 4, point number 5, and point number 6, where we're going to go all the way back through, and then we would go back over to point number 1. We won't go through the development of fluxes on each one, but I am going to go and highlight something on every single one of these. The thing that I do want to go and highlight is just the fact that over here we've got a north pole with its center right over here. We're going to move the center one over on the next one. We've got a north pole with its center over here. Moving on to the next one, we've got a north pole with its center over there. Moving on to the next one, we are going to go and have a north pole with a center over here. And moving on to the next one, north pole centered over here. And then moving on to this one, north pole centered over here. And from there, we would move back to point number 1. So we are going to go and have this rotating field. If I click through them fast enough, we should sort of see the rotation. Look at that. You can watch that north pole kind of rotate around from one point to the next. Low quality animations, but you would expect nothing less of me anyways. So this establishes how we now create this rotating magnetic field. This field is going to be ripping around at whatever speed we are going to go and have placed it based upon the number of poles and based upon the frequency that we are going to be applying to this as well. And the speed that this field is going to go and rotate is going to be something that we are going to go and call synchronous speed. Synchronous speed, we saw this thing developed in generators. They used a formula that used a 120 at that point, and I warned you that there's going to be formulas that use 120 and formulas that are going to go and use 60. The formulas that use 60 are going to be dealing with pole pairs of poles, and the formulas that are going to be using 120 are dealing with individual poles. I would count one pole for the north, I would count one pole for the south. Over here, if we want to go and calculate, the speed of any of our motors or what the speed of the field is that's going to be rotating, that is going to go and give us a pretty good idea as to how fast our rotor is going to go. Now, our rotor is never going to be able to go and catch up to the synchronous speed. It's always like a dog chasing its tail. It can never get there, which means that we're always going to be sitting something a little bit below that. But I can, by telling what my synchronous speed is, have a pretty good guess as to what my motor is. And if I take a look at my motors, I can usually go and figure out from the RPM of the motor what that thing would be for an actual synchronous speed, which would tell me the number of poles. Here's the formula we're going to go and use for synchronous speed, and it's going to give us a speed that is going to be based in revolutions per minute. All I need to do is I need to multiply in the frequency of my supply current in hertz, multiplied by the number of pairs of poles per phase in the motor. So looking at this one over here, the number of pairs of poles per phase. So I'm going to look at the A phase. If I'm looking at the A phase alone, let's erase everything else here because we don't need that. All I'm looking at is my A phase has got one pair of poles that I'm going to go and see over here. Okay, I don't count the B, I don't count the C, because the formula is for the pairs of poles per phase. So I'm not going to go and say that this motor over here would have 3 pole pairs. Once again, how many of these can be at a peak at any given time, and how many places were centered on all of our rotating fields? The answer is always going to be 1. There's only one point where the field is going to be centered around, and only one of these that's going to be at a peak at any given time. So we are only ever going to trace around that center, or a single pole pair at a time. For that previous one that we were just looking at, we can go and figure out what the synchronous speed would be. If we have a 60 hertz system, we would go and say that 60 times 60 is going to go and give me my top part of the A thing there. So this is going to be my frequency. This is going to go and be a constant for the formula. Over top of the number of pairs of poles, which is going to go and be 1, which would tell me that my frequency for that one, or the speed, the synchronous speed for it, would be 3600 RPM. Now, that's going to tell me that going around the inside of that, this thing is going to go around there 3,600 times per minute that we are going to go and spin that field around. Would give me a wicked fast motor rotation if I could go and catch up to it. We do have motors that will operate at ridiculously high speeds. But more than that, this formula also shows me that if I vary this value of frequency, and we're going to talk about this later on when it comes to drives, if I vary this value of frequency, I'm going to be able to go and get all sorts of different RPMs. Imagine if my frequency was only 1 hertz. If my frequency was 1 hertz, I would then go and have this changing to 1 times 60 divided by 1, which would be 60 revolutions per minute. In other words, 1 revolution per second that I would be seeing. And I could go and up my frequency. I could take it up to 10, 15, 20, 30, 40, 50, 60, etc., which is going to go and give me a rise on my speed that is going to be directly proportional to any sort of a rise on my frequency. This is another one of the reasons that we really, really love our 3-phase motors, is because we can throw them onto that variable frequency drive if they're rated for inverter duty, as we said before. And then we are going to be able to go and adjust them from 0 RPM all the way up to whatever their maximum RPM is. And if I go above that, and frequency drives can go above that, you can overclock. You usually have to go into some back-end menus to go and unlock it because I don't want to just leave that loose. But I can even take this motor and I can take it up to higher frequencies, 90 hertz or something like that. If I would take this up to 90 hertz, I would now be able to go and take this thing from 3,600 up to a synchronous speed of my field all the way up to 5,400. So we can start to go and get, some incredible speed controls that we are going to be able to go and take out of our motors themselves. Okay, enough about the synchronous speed. We are now going to go and talk about the part of the motor that is trying to catch this synchronous field. And the part of the motor that is trying to catch this synchronous field is going to go and be the squirrel cage. The squirrel cage is going to be these bars that are going to be conductive, that are going to be buried within the iron. Remember, we have got the rotor itself made up of laminated iron. That's all going to be in between here, but then these are going to be made out of copper or aluminum or brass or something like that. And then the same with the rings across the outside. We want to have a high amperage, low resistance type of path that is going to be easy for us to go and stick current through. So how do we get currents into these? Well, we've talked before about that our motor is going to go and be a rotary transformer. In other words, we are going to go and have these 3 fields that are going to be circulating around the outside. I'm just going to kind of draw a couple of blocks over here right now. 3 fields that are going to be circulating around the outside based upon, whatever I have. I got 1 north, I got 1 south, but, these things are going to split. We'll cover all that stuff later on as we need to. These fields are going to be rotating around the outside. We've got that north that it's going to be chasing, but all of these, as we go and send current through them, looking especially back at these over here, you'll note that we are sending current through these, therefore we are creating magnetic flux. And that magnetic flux is going to be coming directly from one field pole, shooting over towards the other field pole. I'll actually draw it with just the 2 poles over here. The split poles, by the way, all that these would be doing is that we're going to have maximum current or maximum magnetism. Some goes in like that, and then these would go in like that. And so what we see is we would have this one, if this one's going to be my one that's magnetized right now, it's going to have maximum. These other 2 are going to be smaller, but it's going to be easier if I actually just utilize just a different look to this. And if I just talk about the single north and a single south, okay? We're just going to pretend like we've got all 3 of these mashed together, creating 1 large north and 1 large south that we are going to have. Because we've got this large north and because we've got this large south, go back to these. If I've got a large north, I've got a large south as well. I'm going to be able to shoot those lines of flux across from one side over to the other. And as those lines of flux go across, they're going to go and cut through those metal bars. Those metal bars are then going to go and induce a current in them, provided that there is relative motion. Remember, though, that this whole field is rotating, so there will be relative motion. If this rotor is at a standstill, right now, at the instant that we start, the field is whipping around at synchronous speed. Therefore, there is going to be relative motion across them, and I should be able to go and develop current inside of these bars over here. Here's what it goes and looks like. What we're going to do is we're going to go and examine these two bars right over here. We're going to examine these things with the left-hand rule. First thing that we are going to do is we're going to establish a bunch of directions off of here. So we see this, that is going to be my clockwise rotation of flux. We're going to start with the left-hand generator rule, which is going to be thumb for thrust, first finger for field, and center finger that is going to be for my current. We have to go and take a look at thrust. If we're dealing with the left-hand rule, we keep our center finger folded in. We're looking at our first finger, which is going to be direction of field flux, and our thumb, which is going to be direction of thrust, are what we have to start with. But we have to start with the thrust on the conductor. If our field is moving in this direction, it would be the same thing as if my conductors were moving in this direction, moving up and away. I'll do that with a red marker so that we can see it a little bit better. So it's as if my conductors were moving up and away in that direction. We've also got complete lines of flux that are going to be formed. So from my north pole over here, I see that I'm going to have lines of flux that are going to be traveling through. They're going to travel through into the core of the rotor through the steel laminations. And then they're going to come back out onto the south pole, and then they're going to go through the motor itself and form that complete path like that. This is what we're having on each one of these. Same with on this one over here. Not through the bars itself, going to go into the core of the rotor itself, going to come back out of the core of the rotor, up through my south, back down through my north over there. So these green ones are going to be my first finger. They're going to be my direction of flux. My thumb is going to go and be in the direction of thrust. And we're going to start by analyzing this bar right over here using the left-hand rule. Put your first finger in the direction of flux. Stick your thumb in the direction of thrust. You can rotate your page a little bit if you want to. And then when you fold out your center finger, you should see that your center finger is heading away from you. So if I were to look at this thing as a cross section, I would see that it's heading away from me, therefore it's heading down that bar in that direction. Let's take a look at this one over here. In this one, we've got the lines of flux that are coming through in the opposite direction. Right? They're coming through from starting inside of here, flying through to my south pole like that. I've still got my thumb in the same direction. And now when I go and fold out my center finger, I should see that this one over here is going to have a current that is heading towards me. And so we can go and highlight that one as well. We've established those directions of current that are going to be on each of those. So far, so good. This is going to be my generator. Value of current that I'm going to go and have. Remember, it is a transformer. So we are taking energy from whatever my source is, converting it to magnetism. As it then cuts across here, it is then going to create current flow through these shorted out bars. Perfect. Once we have that, the next thing we need to do is we need to take a look at what happens around each one of these. Okay, I'm going to remove this little arrow here. I'm going to keep these green arrows over here because those are going to be my direction of the field, but we're now going to go and take a look at these individual bars. I want you to use the left-hand rule on your bars, but this is not the left-hand motor rule. This is the one where you stick your thumb in the direction that the current is flowing and then your fingers curl around in the direction that the field is rotating. You should see that this bar over here is going to go and have current that is going to be rotating around it in that sort of a direction. Same with this one over here. If you use your left-hand rule, you should see that you are going to go and have current that is going to be heading around this one in this direction, opposite. Like that around there. What is that going to do? Well, this is going to go and catch my lines of flux, and it is going to go and stretch them. You remember that analogy I gave you guys earlier on where we were talking about power takeoffs, right? PTOs, and the way that they grab lines of flux and they can go and, or sorry, not PTOs grab lines of flux, but the way that a PTO, which is a rotating piece of machinery, can go and grab onto something and pull it around in the same direction. This is going to go and do the same thing. If I take a look at my lines of flux over here, this line of flux is going to get distorted because it's heading in towards that, but now it's going to get grabbed and caught. Oops, sorry. Put that circle back over there. Let's draw this line of flux. Line of flux leaves from the North Pole, it gets to here. Once it gets here, it gets caught by that, which means it is going to go and circle around like that. And then it goes down and into here. So I see distortion in that direction. I'm then going to go and take it through the inside of my rotor. As I take it through the inside of my rotor, I then fire it back out towards the South Pole over here. As it goes out towards the south pole, it is going to go and get caught by this rotating red field that we have over here, which is then going to go and bend it around like that before releasing it to head back up over there. If I take a look at that, I see that I am going to go and have forces that are going to be acting in this sort of a direction. They're trying, because we've got these magnetic lines of force that are distorted like that, they're going to try to slingshot out each of these fields over here that are currently distorting them. Try to push them all the way out to the point where it's going to be able to go and rotate. And we see that that ends up being my direction of force on the rotor. That the rotor itself is now going to be pushed because each of these magnetic lines of flux, which cannot cross but can only be distorted, is trying to get pushed out. That's the direction we end up running these off at. It's really just a fantastic looking thing when you take a look at it. You can use your right hand rule, by the way, as well. If you're using a right hand rule, what you would have to do is you'd have to fold down your thumb, because the last thing that you're looking at is your thrust, but you'd have to use your first finger in the direction of your field. So going through from north to south, and then you'd have to use your center finger in the direction of your current. So if you want to use your right hand rule, you would stick your first finger aligned with the green arrow. This would be your first finger. You'd stick your center finger facing into the page. That would be aligned with your current. And when you do that, finger pointing down, current going in, you would see that you would have a thrust. Your thumb would fold out in the direction of this blue arrow that we see over here. Okay, that is going to go and give us our push that we are going to go and have. Now let's go and talk about something called speed and slip. Speed and slip are going to go and be the ways that we relate the synchronous speed to the actual speed that the motor itself is going to be running at. First of all, before we even start analyzing any of these, no load speeds, full load speeds, and rotor speeds and stuff like that, we have to recognize the fact that we will never, ever, ever be able to go and operate our motor at the same speed as what our synchronous speed is. If we manage to go and get our motor up to synchronous speed, there would be no relative motion. If the rotor was moving at the same speed as what my field was around the outside, there would be no relative motion. And if there was no relative motion, there would be no cutting of flux lines. If there's no cutting of flux lines, there would be no generation of voltage and current and motor effect. So we're always going to go and have some difference in speed between what the actual motor is and between what the actual rotor itself is, from synchronous speed to the other. There has to be relative motion. And note that it doesn't have to be, a lot of relative motion, but there has to be some. You can envision this thing by, thinking about something like a racetrack over here. We'll just draw a big old racetrack. And if I have got two vehicles that are traveling around the racetrack, oh man, you guys are going to judge me harsh for my drawing abilities now, but whatever. Car over there traveling around the racetrack. We're going to stick another car that is going to be going around here as well, around the racetrack over there. What we'll see is that there has to be relative amount of motion. At the instant of startup, let's just pretend that this one over here is going to be at a standstill, where this one is going to be rotating around that track at 60 times per second, okay? That would mean that there's going to be a massive difference in speed between this one and between that one. But as I then start to go and speed up on this one over here, as this one starts to go and pick up and start to draft around, as long as there's still going to be some sort of a relative motion, I'm going to go and take this one here, we're going to put this one down at 57. 57 revolutions per minute compared to 60 revolutions per minute is going to be, a small percent difference. But it's going to be enough that we know that consistently this one is going to be overtaking, passing, and lapping the other one. And that's really all that the synchronous field needs to be doing, is it needs to be lapping the rotor so that we can then go and generate that difference. If we don't have generate any sort of difference, we're not going to go and generate any sort of value of voltage on those individual rotor bars, the actual squirrel cage bars that we need inside. And if we don't generate the voltage, we get no current and magnetic field to go and pull that thing through. So let's go and talk about the relative speed between the rotating stator field and the rotor. This is going to be called my slip speed. And my slip speed is just going to be my synchronous speed minus my rotor speed. So in this case, my synchronous speed would be 60, my rotor speed would be 57, therefore I would have a slip speed that would be 3 off of this one. Now if we put it into actual motor ones, let's go with one where we have got a 1800 RPM synchronous, and we'll go with 1735 as being my actual RPM. That is going to go and give me what we can refer to as my percent slip as well as my slip speed. Slip speed for this is just going to be my 1800 minus my 1735. So 1800 minus 1735 tells me that this thing has got a slip speed of 65 RPM slip speed. Okay, it's an actual speed given in RPMs because it's a difference from my synchronous to my actual. This is also going to be able to go and be taken as being a percentage or a percent slip that we are going to go and have. Percent slip is going to be synchronous minus my rotor speed. So this is 1800 minus my rotor speed, 1735, all divided by my synchronous speed, 1800, that I'm going to go and have over here. Take that, it's going to be 65 over top of 1800. Let's just pull up a calculator over here. Just delete that, 1800 minus 1735 divided by 1800, which gets me out to a value of 3.6. This is going to be a percent because we can just take this now and multiply it by 100. 3.6% that I would go and have for this one. The bigger the percent slip, the more that this thing is going to go and be past, that our synchronous speed is going past the actual rotor itself. When our percent slip is high, it's going to be whenever my rotor speed is going to go and be low. And percent slip is going to go and change throughout the run of a motor. If I were to compare it between full running, which is going to be 1735, between the instant and startup. At the instant of startup, my synchronous, actually here, I'll just sketch it out over here. Startup. Startup would be me taking this thing and instantly turning it on. I'm going to go and have my field that is going to be running at 1800 RPM. And instantaneously, I'm also going to go and have my rotor that's going to be at 0 RPM, the instant of startup. So I'm going to go and have a massive slip speed. I'm also going to go and have a massive percent slip that I'm going to go and have. What I'm going to see is I'm going to have 100% slip, right? I'm not getting any rotation. But then as this thing starts to go and rotate, it's going to go and continue to build speed. I'm always going to go and have 1800 RPM at full speed. But I'm now going to go and have 1800 RPM for my synchronous, but my full speed would be 1735. And so what I'll have seen happening between startup to full speed is that I'm going to have gone from 100% slip down to 3.6% slip that I'm going to have off of this motor over here. So the slip is going to go and change, or the percent slip is going to go and change as I operate the motor. As I add load onto a motor, the RPMs are going to go down, which means that I'm going to go and have more percent slip that is going to go off of that as well. This brings us to another thing that is going to go and be called my speed regulation. Speed regulation is going to go and be the difference between how my motor does between no load compared to its full load. And we have done this before, this percent regulation. We have seen this for voltage regulation on generators. We've seen it use the same formula over and over again, which is always going to be no load minus full load all over top of my full load. Once again, if we go and take this thing, we can say, what's my no load speed? So if my motor is rated at 1735, that is probably going to go and be its no load speed, so 1735. This is an actual speed, not the synchronous speed, because the synchronous speed has to be faster. When I get this thing all the way up to full load, this one here might be operating at, let's go and say 1690 RPM. So what I would do is I would say no load minus my full load, all divided by my full load, is going to go and give me my percent speed regulation. bracket that out, 1735 minus 1690 divided by my full load, so 1690 again, would go and get me out to a value of 2.6%. You multiply by 100 to get to your 2.6% that we would have for this motor. Okay. These numbers, by the way, the 1735, the 1690, and the 1800 that I've been working with are just numbers that I have made up for the sake of being able to go and do calculations off of these ones here, okay? There's nothing in the book that said that we had to use those ones. These were just ones that I wanted to go and utilize for the sake of just making some calculations, etc. For speed regulation, what we do want to go and see is we want to see low. Low is good for speed regulation. Just write that next to the title on speed regulation. The lower the speed regulation, the better that motor is, because it means that there's a smaller change going from my no load over to my full load back and forth. And this is good because it means that my loads are going to go and see a much more steady utilization of their power and rotation, etc. Okay, reversing rotation. Reversing rotation can be done by interchanging any two line leads. If I were to go and reverse my rotation and change my A to my B and go through all 6 of these steps again, what I would see, what I would see off of it would be that my direction of rotation, rather than going around like this, that we had this counterclockwise, oh, I stepped one too far there. Instead of this going around this counterclockwise, we would have rotated this thing around in the opposite direction, would have gone in a clockwise type of manner that we would have had. You interchange any two line leads. Now, it can be absolutely any two line leads. However, the standard is that you are going to go and interchange your lines A and your line C. And the reason that we're going to go and interchange line A and C is simply this. Look, we've got A, B, C. What is A, B, C? I don't know. What is C, B, A? Well, once we take a look at both of these together, you should recognize these as being my standard 3-phase rotations. What do we note stays the same? B stays in the center. We go ABC or we go CBA. So generally speaking, the de facto standard for interchanging is going to go and be that if I must interchange any two lines, I'm going to interchange A and C so that I had to go from an ABC rotation to a CBA rotation. Yes, we could go and interchange and go from, change A and B and have a BAC, but that's a non-standard rotation. It'll work. Nothing going to be wrong with it, but it is non-standard. All right, let's go and talk about speed torque current characteristics and the relationship between them all. Because if we take a look at this formula that we have over here, it shows that we have got a relationship between the actual build of the machine, the K, the constant of the motor, the amount of flux that I'm going to go and have in the stator or produced by the stator, the amount of current that I'm going to go and have inside of the rotor. This is going to be measured in amperes, and it's going to be the actual current going through the rotor bars. Obviously, the stronger the current that is going through the rotor bars, the more that is going to go and fight back against the flux that I'm going to go and have on my stator, which is then going to go and give me more torque or more twisting force out of my motor itself. The last thing that I'm going to go and have is going to be this cosine of theta. It's going to be the power factor of the rotor circuit itself. Now, our power factor is going to go and change a little bit as we go throughout our rotation, because we're going to go and have differing components, either resistance or reactance, that are going to be seen as being part of my impedance. Generally speaking, when we start taking a look at the stator itself, starting on the outside, the stator, because it's going to be the primary of my motor, which is also acting like a transformer. If we take a look at the stator windings themselves, and we'll stick a couple windings just real quick onto here, those stator windings are going to be having their voltage limited by the amount of counter EMF that I'm going to be able to go and build up inside of them. We are going to go and have current that is going to go and flow through these. As the current flows through here, we are going to go and get a countering force, counter EMF, as laid out inside of your second year schooling, that is going to go and push back against them. The formula for that is this one over here. E is equal to negative L delta I over top of delta T. Change in current over top of change in time. multiplied by my inductance value in Henry. Remember that these are coils, therefore they are acting as inductors as well, which is going to go and give me a counter EMF. And if we take a look at a sine wave, we know that for any sine wave, the maximum rate of change, the amount of change in current over top of change in time, is always going to take place whether it's going to be at its steepest. Therefore, we are going to have the maximum amount of counter EMF right there when we are going in a drop on our feeding line or on a rise on our feeding line. And we're going to go and have a minimum amount of counter EMF right over here, where we have got very little change in the magnitude of current over top of the change in time. So as our current flows to the stator winding, it's going to go and create this counter EMF. And counter EMF comes with its own flux. If you go back once again to your level 2 materials, and I said at the very beginning of this that you should make sure you're reviewing that, you'll go through a bunch of vectors inside of there. And generally speaking, we don't use a lot of our vectors for everything inside of this course, at least not the way that I teach it. But in this case, it is really handy. And it goes through this whole thing that, look, if we have got our E applied to any sort of an inductor, we are going to go and have an E counter EMF that is going to be in the opposite direction. And then later on, when we went into transformers in second year, once again, we went and we took a look at the secondary value of voltage. Whatever I had for my V secondary was also going to be in the same direction as the counter EMF that was going to be on my primary. This is important to us, that we are going to go and see that whatever we have for counter EMF is going to be in line with whatever we have for secondary current in a transformer. Because once again, we are talking about something that is acting as a transformer. Remember, we have got this rotor on the inside that's acting as the secondary of our transformer. Because we are generating voltage inside of our rotor over here, we're also going to be creating current as that current goes through the actual rotor bars down to the outside rings, flows back down the rotor bars down to the outside ring as well. Which means that each of those currents is also going to go and have its own flux that's going to be fighting back against the applied flux that we are going to go and have. What this is going to do is it's going to go and cause a disruption in the main field flux that we are going to go and have over here. And it's going to have to create a rebalancing, basically, of all of our different values of voltage and current inside of there. Any change in rotor current is going to have to be matched by a change in stator current. And I know that what we've gone through over here with all of these, different vectors and stuff going back and forth can be a little bit confusing when you look at it. But if we want, we can simplify the whole thing down to this formula that we've had before, which was just going to be my kVA in is equal to my kVA out that I'm going to go and have. In other words, if I have got a large amount of current that is going to be flowing inside of here, that's going to be the secondary of my transformer. Remember, motor is a transformer. I'm going to have a maximum amount of current that's inside of there. Therefore, I'm going to have a corresponding large amount of current that's going to be going through my primary windings as well. When are we going to have this maximum? Well, we're going to have this maximum when the rotor is at a standstill, at a dead stop. And this is just going to be based off of this formula that we're well familiar with there. EG is equal to BLV, beta length and velocity. We will generate our maximum value of voltage in the rotor when we have got flux density, which we're always going to go and have inside of our stator. When we've got length, which we're always going to go and have inside of our rotor. Not a lot of length, it's just a squirrel cage, but it's there, it's fixed. And when we have got velocity. And we're talking about the velocity of the field, that field that is moving at synchronous speed, that is spinning around the rotor. At the instant of startup, there's going to be a huge relative velocity difference between the rotor and between the stator. And therefore, we generate a large value of current, a large value of voltage, which is going to go and give us a large value of current. And since we treat this as a secondary of a transformer, that means that if we've got a lot of current in here, we have to be bringing it into the motor as well. So we are going to go and have a maximum value of current that is going to happen when we are going to be at a standstill. This does not mean that we are necessarily going to go and have a maximum value of torque, because although we have got a really, really high value of rotor current here right now, we are also going to go and have a really, really, really low value of power factor on that rotor. Rotor and stator currents are at maximum. Power factor is going to be at a minimum, which means that the overall net effect is going to be counterbalanced. The resistance of my rotor is going to go and be just the copper, right, that we're going to go and have. If I take a look at my squirrel cage that I have here, and let me just erase a couple of these, we'll talk about the frequency for a second. For my rotor, I'm going to go and have all the different bars that are going to be inside of there. We're going to go and have, the squirrel cage. Resistance is going to be more or less a fixed value. But my XL, or my inductive reactance, is going to be a changing value. That is going to go and change as we change our value of rotor frequency. If you remember this formula over here, XL is equal to 2 pi F and L that we are going to go and have here. And this is just going to tell me that the inductive reactance of anything is going to be equal to 2 times pi times frequency times the length. Well, what is the frequency at the instant of startup? I am going to go and have this field that is going to be spinning around here at 1800 RPM. That's going to go and give me a really, really high amount of frequency that I'm going to be cutting through these with. But then as this thing starts to go and pick up, we're going to now bring this thing up. Let's say we take it up to 1700 RPM, and if our synchronous speed is 1800 RPM, we are now going to have dropped that frequency, or the difference that we have in between these, down to 100, which would mean that my XL would also be dropping correspondingly. What we see is at the instant of startup, because we have got that locked rotor and we're going to have that maximum value of frequency over there, at the very instant of startup, we are going to go and have this really, really, really tall value like that. And it's going to have an impedance, a Z, an XL that's going to be really tall, and then it's going to go and have an R that is going to be relatively small, just the resistance. And as my rotor comes faster and faster up to speed, we are going to go and shorten. We're going to keep the resistance the same, but we are going to go and shorten down this overall triangle in a bunch of steps. It's going to happen smoothly as it's running, but it is going to go and drop. Because I am going to be dropping this value of impedance, that means that I am going to go and allow more currents to go and flow through my rotor over here as well. At the instant of startup, we don't have that much current that's going to want to flow because we've got such a crappy power factor. We've got the big triangle, but as we go and speed this thing up, we are going to have the ability to flow more current, even though we have got less frequency, even though we have got less voltage that is going to be generated at any given point over here. What does this do to our motor? Well, for our motor, it is going to go and develop these wonderful lines that we are going to look at over here. These lines over here show a single motor's operation. And there's a couple of things that we are going to go and look at. The first thing we're going to look at is what this bottom row is, which is going to be percent rotor slip. 100% slip would mean this is where the motor is stopped over here. 0% slip would mean that that motor would be operating at synchronous speed. We're never going to have it operating at synchronous speed, so we're never actually going to go and hit that one, but we'll try to approach it. Synchronous over there. The other thing that we're going to take a look at is we're going to take a look at our current. This is going to be my current in amperes. At the instant that I'm stopped, because I'm generating a large value of voltage across there, e.g., is equal to BLV. At the instant that I go and start up this motor, I'm going to have maximum value of voltage in my rotor, which means I'm going to have maximum value of current in my rotor as well. I'm just going to go and have a really, really weak or crappy power factor. Over here, they're showing the power factor line, which is corresponding with this side over here. So we see our power factor is going to be starting out, about the 20-ish% over here, and then the power factor is going to be rising as that XL drops on our motor. We see that our current starts out high, but our current is going to be dropping as our motor gets closer and closer towards full speed. The last thing that we are going to see is we are going to go and have torque off of our motor that is going to go and follow this curve. That's this knee-shaped curve over here, where I am going to go and have a maximum value of torque that's going to go and happen at some point inside of here. Some percent rotor slip is going to be the magical number where I am going to have current in amperes that is going to be matched by a really good power factor, and altogether it's going to go and develop this really, really good torque. And the torque is once again going to go and be off of the K, the phi, the I, and my cosine. And we see that, the higher my cosine, the better my cosine is going to be, the power factor, and the better my current is. Relatively high, not too low, then the better that I'm going to be able to go and create a torque out of that one. Okay, so that's going to be my torque value over there. Right now, when we have got lots of XL at the very beginning moment of startup, we start out with a really crap power factor, but with a ton of current. That's going to be our green line. We're going to go and follow over here. But then as the motor started to go and rotate, the percent rotor slip starts going down. The motor starts catching up with the synchronous field. And eventually, we're going to go and hit the point where my motor itself is going to go and be at what we would refer to 100% torque over here. 100% torque is going to be when it's delivering its rated amount of torque. When it's delivering its rated amount of torque, I can see that this is going to be a value corresponding to a fairly decent power factor over here. It is going to have relatively low value of current right over there that we are going to go and see. And it is going to go and give me my full 100% torque off of this. And this is going to go and happen when I've got a slip that is going to go and be fairly close to this end over here. If you refer to your binders, they talk about this, the full load torque, that this thing is going to go and happen somewhere where we're going to get our 100% over here between the 2 to 5% that I'm going to go and have for my rated 100% torque. If I slip back from there, my motor starts to slow down and bog that thing down, what's going to actually happen is my motor is going to go and fight back. I see that my torque value starts to go and rise, and I'm going to go and reach a maximum torque. That is going to go and happen somewhere about 25%. Now, this is a general rule of thumb. It doesn't apply to every single motor, but by and large, most of your squirrel cage induction motors are going to go and hit their maximum about that 25% over there. This maximum torque that I'm seeing over here is also going to be what we're going to refer to as my breakdown torque. In other words, if I go and ask for more than this torque value, I'm going to erase a bunch of lines over here right now. If I go and ask for more than this torque value out of this specific motor over here, it's not going to be able to go and deliver. It can deliver all the way up to that. Past that, then it is going to go into a stall or into breakdown torque. We'll use either one inside of the industry, but generally speaking, we're going to use the term stalling torque or breakdown torque for it. Starting torque is going to be relatively high as well on most of our motors, not every single motor, but we are going to go and have, if we take a look over here at our 100% slip, we are going to have a torque value, and I'll just carry that all the way across over here. We are going to go and have a torque value that is going to be sitting a little more than 100%. So a little bit more than what I actually need to go and have to run that motor. And I see that it's going to go and increase as my slip goes down. And then once I hit that 25%, then it decreases down until we hit that 100% value over there. On standard squirrel cages, it can be anywhere kind of inside of this range. We will go and see as low as 70%, which means we might have some that are going to start lower than what they actually are able to deliver at full run. And we're going to have others that are going to be able to start way, way high up top, where the torque curve is going to just be turned and it's going to be coming across, relatively flat like that. Different motor characteristics, different current characteristics that we're going to have with each one of those, and therefore they're going to be different motors as we go through. Okay, let's talk about Nema design standards for our squirrel cage induction motors. This next graph over here shows 4 torque curves. We're not looking at current curves. We are not looking at any of the rest of the stuff that we had off here, power factor or anything like that, because the power factor and the current curves are going to be more or less the same for these. It's the design of the rotor itself that is going to go and give us these individual classes that we have. Design A and Design B are going to be termed as being our standard types of motors over here. Of these two, the Design B is going to go and be my most prevalent, my most commonly used one. And we see that this thing is going to go and start out higher than that 100% torque, and then it's going to go and increase at about 25% over there. It's going to go and reach its absolute maximum. At the instant that it starts out, 100% slip over here, it starts out relatively high, it decreases a little bit, and then it goes and does this climb again until we hit that 25%. And then after that, once we get into the 100% rated range, it's going to be pretty similar to a lot of the other types of design classes that we have. Design A is very similar to a Design Class B, but Design Class B is going to go and have restrictions on the starting current. We're going to go and have just a better build on it that is going to go and give us less inrush. But for the rest, if I take a look at those two curves, they're going to be relatively similar. Design A will have a slightly higher torque value just due to the fact that it is going to go and have a slightly higher amount of current that it is going to be able to carry through. For my design A and B, both of them have got a starting torque right over here that is going to be lower than their breakdown torques, which are going to be right over here. Which means that they're going to be used for loads that do not go and take, a huge amount of starting torque to go and start up. It's still going to go and be higher than its running torque. If I take a look, we're well above that 100% running torque, but it's not great for doing a lot of high torque starts. Design class C, it's going to be this one over here, has got a starting torque that is going to go and be higher than its breakdown torque. It's really good when I have got something that's heavy that I have to get started up, but once it gets moving, it's going to be all right. Things that have got heavy flywheels, crushers, drums, things like that are all great candidates for this design C because it's hard to get started, but once it gets started, it doesn't need to work as hard, and therefore I'm able to go and relax my torque curve in these as well. Design class D is going to go and have our absolute highest values of breakdown torque. It's also going to go and have a fairly decent amount of inrush, but if I take a look at my design class D, I'm going to see an extremely high starting torque. Right now, this one that they are graphing out for us shows us a starting torque that's going to be about 275%. It is going to go and start high. It's going to go and break down at about the same high type of torque values. And it is going to go and be an extremely tough motor as far as running goes. We're able to go and get these things started. They're able to go and power through loads, and they're going to go and fight back against any stallouts. Anytime that we've got high inertia loads, super high inertia loads that are going to be critical, then we are going to go and utilize these, but only if the speed variation is not going to go and be all that critical to us. It has got really poor speed characteristics. Poor speed characteristics. Meaning that as this thing goes from a no load all the way up to a full load, we're going to get a really, really drooping speed characteristic. Very similar to what we would go and have for a series type of motor. Not quite as bad as the series type of DC motor, but it's going to be, fairly high like that. What I do also note about it is that this is going to be a high resistance, high R rotor that I'm going to be using for this. Meaning that at the instant of starting, I'm going to have a fairly high R, I'm going to have a fairly high XL, but I'm going to have a pretty decent power factor all the way along. And I do want to note as well that this high resistance that we are going to go and see inside of this rotor, we're going to spoof that thing later on. Later on, we're going to go and take a look at another motor that's going to go and have a rotor where we can change the resistance. It's going to be called the wound rotor motor, WRM. The worm. The wound rotor motor is going to have a rotor that we can start out in these characteristics as a high resistance. And then as this thing gets closer and closer to running, we can start dropping out the resistance and we can actually change it over from our design D. We can change it over while it's operating to a design B, which is going to have better current characteristics and it's going to go and have better speed regulation that we are going to go and have. Okay, on to another type of formula over here. We're going to talk about motor efficiency. Efficiency is just going to be the ratio of my power out compared to my power in. Every motor is going to go and have a rated horsepower. That is what we're going to go and have for our power out. Rated horsepower. But that motor is also going to go and have other losses. If you put your hand onto a motor, you should feel some heat coming off of it. So I'm going to have an input power that is going to be made up of my rated horsepower plus whatever losses that I'm going to go and have inside of there. Altogether, the power out, the amount that I'm taking out on the shaft, the rated horsepower, over top of the power in, the horsepower that I'm delivering, plus my losses that I have to account for, is going to go and give me my efficiency. Multiply it out by 100, we're going to end up at 8% efficiency. They do give you a couple of formula or a couple of examples inside of your book. Just go through those examples. Make sure that you're good to go on how to calculate this. It is a very common calculation, and I would not be surprised to find these calculations, first of all, in third year over here, but also in fourth and on interprovincials, on standard level exams, on your FSR exam someday if you decide to become a contractor, become an FSR, etc. So it's a common one. Get used to the percent efficiency. Power out over top of power in. All right. The very last section that we are going to go and talk about is going to go and be my linear induction motor. I'm actually going to go and stop this video right now, and we are going to go and have just a separate one that's going to be the linear induction video.